board. Okay, so what we're going to look at is two similar problems involving finding the area of a triangle given three coordinates. The first problem we're going to look at is in 2 dimensions, while the second problem is going to be in 3 dimensions. So to get started, let's define these 3 points and let's graph them to get an idea of the shape. Clearly, we can see that the 3 points form a triangle and they are not collinear. If these 3 points were collinear, then the area would be 0. So what we're going to do is define 2 vectors from a common point. Let's use the center point here, R, and define vectors from R to P and R to Q. Now, in order to find the area of this triangle, let's first consider the parallelogram bound by these vectors. In order to find the area of this parallelogram, we're going to calculate the determinant of the matrix determined by these 2 vectors. However, we don't want the area of the parallelogram, we only want the area of this triangle. So if we cut it in half, like shown here on the graph, algebraically we'll divide the determinant by 2 to find the area of this triangle. So let's first define vectors from the common point R. And we're going to use this formula. The area equals 1/2 of the magnitude of the determinant of the matrix of RQ and RP. So if we calculate the determinant, making sure to express it as a matrix, we come up with the value of -27. However, in our formula, that's why we have the absolute value, so we could express the area as a positive. So the area of this triangle will simply be 27 divided by 2. Now, if we consider that absolute value in our equation, what happens if we reverse those 2 vectors? The determinant of RP and RQ. the magnitude is still the same, but the sign is positive. So the area of this triangle is 27 halves. We're going to follow a very similar procedure when we look at the 3D example. So in the 3D example, let's first define the 3 points, and let's write 2 vectors using the point Q as a common point. So if we use Q as our common point, our 2 vectors are going to be QR and QS. Now we're going to use a different formula this time for 3D. The area equals 1/2 of the magnitude of cross product of our 2 vectors, QR and QS. Well, why do we use the cross product this time? Well, if we look at one of the definitions of the cross product of A and B is equal to the magnitude of A times the magnitude of B times the sine of the angle between. Now this formula, the magnitude of A times the magnitude of B sine theta, is analogous to our basic formula for the area of a parallelogram, which is simply base times height. Where the magnitude of A is the base, if you take the sine of theta and multiply it by the magnitude of B, that'll give us the vertical component of B, which is the height of the parallelogram. So if we calculate the cross product of our 2 vectors, QR and QS, we're going to get a vector. So we take the magnitude of this vector, divide the result by 2. The area of the triangle is 3 root of 10. Now again, if you notice in our formula, we're using absolute value bars because the cross product is not commutative. So what happens if we do the cross product of the reverse of QS and QR? The vector has the same value, but notice the signs are opposite. However, when we take the magnitude of that vector, the value is still the same. So the area of the triangle bound by these 3 points is 3 root of 10.